Hi, today we'll be talking about day 9 of the HackerRank 30-day challenge. And so remember, day 9 is really the 10th challenge since counting starts at 0 for both Python and C++. Today we'll be talking about looking at recursions or recurrent relations associated with particular problem sets. In this case, we're going to look at the most basic, so the simplest case for recursion methods. And what this is it's going to look at factorial problems and how to implement that within code through recursion. Now you can implement this through an iterative method. Also, it's important to note that the method that we're about to use for recursion is not the method that's commonly associated with competitive programming algorithms, just because it's too slow. And not only is it too slow, it calls too many stacks. Not only that, it also doesn't store big integers properly. So some of the limitations before we go forward with this factorial method implemented through recursion is that in Python, probably similar across C++ and Kotlin, is you can only have 1,000 stacks that are called within a program. So what that means is if you start with the number n and you try to figure out the factorial of it, well, you'd be doing n times n minus 1 factorial. So you would essentially start with n and call the method itself, so call the function itself back. So n minus 1 is now the parameter, and then you go to n minus 2 and you keep going forever as long as it doesn't equal 1. Once it equals 1, then it stops, and that's the breaking point. But let's say this is 10,000. Well, essentially what's going to happen is you have to call it more than 1,000 stacks, and so it gets very slow, and the operating system has to keep up with making sure that it's calling the stack above it. So in this case, the stack above it is going to be n minus 1 and n minus 2, n minus 3. And if you know anything about programming and assembly languages, especially when you're working with stacks for, I guess, stack memory or heap memory, the stack grows, and it grows from the base problem. And so what happens is you then have to allocate more and more memory, and it grows, upward, if you want to consider that. And what happens is when it grows too much, then you could have stack overflows or it runs out of memory. And so the reason why this method in particular is not very good is because it's calling a recursion function multiple times, and essentially you're running out of space to utilize. There's more technical nuances associated with, especially when you're considering stack versus heap. And that's not something we'll talk about now. We'll be talking about it later. So in the future, I'm going to be going over buffer overflows. And I'm going to be looking at stack versus heap memory associated with both wireless hacking and hacking within an enterprise. So for the LPT, which is licensed penetration tester, you have to be intricately aware of stack versus heap and how that's represented within different registers and how that's represented within, I guess, your machine down at the lowest level, so at the machine code. However, for basic beginners, just consider that, once you grow the stack to a certain percent or to a certain amount, it starts running out of memory. And that's what we're going to see here. A few implementations that are done for competitive programming is essentially running it iteratively, so running it through a for loop. Also, that for loop is going to store it in an array, and that array can continue to expand. And what it does is it doesn't call what the previous function is. What it does is it calls the previous 2 slots within the array to continue growing the array from the previous 2 recurrent relations. And so in that case, t minus 1 and t minus 2 from that particular value t. And another common implementation to make this faster is running something called a cache, which is essentially caching any stored value that's already been seen. So if you're running GCD and you're trying to figure out the greatest common denominator across multiple factors or multiple variables, then you could store a cache to essentially make sure that you haven't already computed that value, which will save your runtime. Once again, that's something we'll cover later. It's on my GitHub. You can look at it. So what we've looked at so far is that recursion is slow. It runs out of memory very quickly because you only have a certain amount of stacks you can, or I guess, times you can call a particular function within programming languages. It grows a stack too much where you run out of memory addresses. Not only that, we want to implement it with an array so that we can continue growing for large integers. Also, it allows us to look at recurrent relations from t minus 1 and t minus 2. T is going to be the value that we're looking at. And then we're storing caches or cached databases so that we can call those operations that we've already done previously so that we don't have to recompute it. So let's go through the code really quickly. We have about 8 minutes left. I want to show you Python, C++, and Kotlin. Here are just think of them as header files. So you're importing different modules associated with math, OS, random, regular expressions, system. We're not going to use most of them we're not going to use any of them in our function that we have to implement. However, they are used to filter the input and then store that input within whatever we're writing it to. So let's talk about recurrent relations, and let's talk about recursion. So in this situation, we pass the value that is inputted. So we input 3, and 3 doesn't equal 1. So we go on to the next statement, which is going to be an else. So think of it as your final execution. And we're returning 3 times the function itself with the parameter 3 minus 1, so 2. So we put 2 back into the function. And remember, this is how we're growing stacks, or if you want to consider it at the operating system level, it would be growing up. And so 2 doesn't equal 1. 2 times factorial 2 minus 1 is going to be 1. Plug it back in. So this statement does come out to be true because 1 is equal to 1. So you return 1, and this is where the system has to call back its previously computed values. So now 1 times 2 times 3 is going to be 6. And that's what we'll see here. And so we'll just run through continuous test cases. Once again, instead of having the system store that memory at a certain address or store that operational result at a certain address, we can store it within an array to essentially just call the previous memory addresses t minus 1, t minus 2 if it's a continuous sequence. If it's non-continuous, once again, it would just call the memory address associated with t-1 and t-2. Going further, we'll talk about C++. We've covered left trim and right trim multiple times within previous videos, so just look at those. And in this case, we're using the standard library as our namespace, so we don't have to include std : for namespace resolution throughout the program. It's just taking in input, filtering that input, and then passing it to our factorial function. Once we get a result from that, we can then write it to the system and then close the file. So in this scenario, let's go through our C++ function. It's going to look almost the same in Kotlin. In this scenario, 3 is inputted. If 3 is less than or equal to 1, you stop, but it's not, so you go to your final clause or your else statement, and 3 times factorial 3 minus 1, which is going to be 2. You put it back into your factorial function, and 2 doesn't equal 1, and so once again, 2 times factorial 2 minus 1, which is going to be 1. Put it back into your factorial function, and 1 does equal 1, so return 1. 1 times 2 times 3 is going to be 6. And so the system has to accommodate for all those functions that were recursively called, and they have to store the immediate results. So when you have a very large number, those recursive calls could actually go larger than 1,000 calls, recursive calls, and your system may say it's too large. So that's why we store the values in an array. Now we're looking at Kotlin. Kotlin is very similar. The syntax for inputting and stripping the function, and then essentially writing it to standard out is a little different, but it's going to have the exact same syntax as C++, with the exception that you need to define your parameter and your return value a little differently in C++, and you don't have to have the I guess semicolons in this statement, both the first one and the second one. Once again, this is very short. I touched upon a lot of things. There are a few things that I would recommend searching and researching more on, specifically how memory addresses are stored within the register, and how stack values are accommodated ahead of time, and how heap memory works. So I didn't cover stack versus heap very well in this video on purpose. I made it very vague. I hope that it was enough for people that are just starting to code. So this is only your 10th day coding, and so differentiating between stack and heap memory is a little premature. If you're interested in it, you can go research more. Once again, it's not required to know that information until 6 months to a year into programming positions. And even then, a lot of the LeetCode and HackerRank problems don't differentiate between stack versus heap-based memory. Only when you're concerned about the programming performance of an application do you really have to be concerned about stack versus heap memory. And when you're doing reverse engineering for malware analysis, do you have to be concerned about stack versus heap memory? If you really just want to consider it that the recursive recalls or recursive calls that are being done through this factorial function are too much, that's enough. Just that it passes 1,000 recursive recalls is enough to tell people and to sound informed on your subject. Once again, we'll cover all these things later. I look forward for you to continue watching my videos, and I hope you enjoy them. Like, subscribe, and comment. Have a great day.